In this video, we'll review energy, momentum, and rotational motion. So I'll start with concepts. So the first concept that is important to energy is what's called the work-energy theorem. So the work-energy theorem tells you that the total work and the total part is important. The total work by all forces acting on an object is equal to the system's change in kinetic energy. Okay, so this doesn't mean that one force is going to equal the change in kinetic energy, but if you sum up the work done by all forces, then you will get the total change in kinetic energy. And so one way that we know the total work is equal to 0 is if delta K is equal to 0. Okay, so that's just writing it in equations, but that's another way of saying you are moving at constant velocity. So if your velocity is not changing, then your kinetic energy is not changing. Okay, and then for momentum, we have a very similar principle. Okay, and this is called the impulse momentum theorem, or impulse momentum principle. And in the same way, this says the total impulse by all forces equals the system's change in momentum. Okay, so the way that both of these are similar is that both state that or require a net external force to change the energy or the momentum. So if there's no net external force acting on your system, then energy is going to be conserved. It's an isolated or closed system. And in the same way, if you have no external forces applying an impulse, then your momentum is going to be conserved. But if you have an outside force, then that can both change the energy and change the momentum. And so both of these also lead to conservation laws. Okay, the next idea has to do with translations and rotations. Translations, and rotations, and the net force and the net torque on an object. Okay, so at this point, when we get to rotations, we start considering the motion of rigid bodies. And so the easiest one to consider is just a rod. Okay, so we want to imagine a situation where this rod can translate but not rotate. Okay, so if you imagine applying two forces, so F1 on the left end and F2 on the right, and F1 is going to be some distance R1 away, and R2, F2 will be some distance R2 away from what would be some pivot point. Okay, so you can imagine if one of these forces wasn't there, the other force could cause this thing to rotate about this point, would have a torque about this point. So F1 would cause a rotation this way, F2 would cause a rotation that way. So if you sum up the forces, first off, let's let F1 equal F2, and let's put them the same distance away from the pivot point. Well, in this case, if you just apply Newton's second law, if you sum up the forces in y, you get F1 plus F2. So that's all you have. And if you set that equal to mass times acceleration, if that's all you've got, and they're equal in opposite not equal and opposite, but equal in the same direction, then that's going to cause a net acceleration. And if you sum up all the torques, well, F1 and R1 are the same magnitude as F2, R2. The only difference is they cause opposite direction rotations. So F1 causes clockwise, F2 causes counterclockwise. And so they're going to sum to 0. And so this is an example of when you could have translation. So this would translate, but not rotate. Okay, and then we could do a similar example and get the opposite case. So now let's move F1 up to the top. So it's up here. It again will be some distance R1 away. And then F2 we'll leave on the bottom. It will be some distance R2 away. Well, now they're both going to cause rotations in the same direction, so their torques will be in the same direction. And again, we'll just leave the F1 equals F2, R1 equals R2. If you sum up the forces in Y, you get minus F1 plus F2, and they're the same size, so they're going to go to 0. So the sum of the forces is 0. If you sum up the torques, well, now they're going to add. You're going to have the torque from force 1 plus the torque from force 2, or R1 F1 plus R2 F2, and that's going to equal some moment of inertia of the rod about this point times its angular acceleration, okay, since this is positive. So this would rotate but not translate. Okay, so you can, in one case you can have your forces add, but their torques cancel out, so you can translate without rotating. And in the other case, the forces may cancel out, but cause a torque that generates a rotation in the same direction, so it can rotate without translating. And then you could have some combination of the two. So you could imagine just having one force applied at the end, some distance from an axis of rotation. If you only have one force, then you sum up the forces, you'll get something positive, or you'll get a non-zero number, maybe in a negative direction. But you'd also get a torque too, because you don't have another force applying a torque in the other direction to cancel it out. Okay, so you can also have combinations of both translations and rotations. Our next idea is impulse. Okay, so impulse has to do with how fast you feel forces and how much they change your momentum. So if you imagine you have a truck and it has some, not initial mass, the mass isn't changing, it has some mass and it has some initial velocity. And then later that truck is going to crash. So draw this the best I can. So now it has same mass, but its final velocity is 0. Okay, so it was going, it had some initial momentum, and then it crashes into a wall. So your impulse is equal to your change in momentum. And so this is PF minus PI, or MVF minus MVI. Okay, so since your final velocity is always going to be 0 and you crash, you're eventually going to stop, your final momentum will also always be 0. And once you start to crash or lose control, you're going at some speed. Once you start to lose control and crash, this is also constant. Okay, so this is always going to be 0 in a situation like this, and this will be constant. Okay, so what that means is your impulse is sort of fixed. Okay, so impulse, it's going to be what it's going to be. Okay, your final momentum will be 0. Your initial momentum is whatever it is when you lost control or before you hit the wall. So impulse is fixed. Or another way of writing that mathematically is just J is equal to a constant. Okay, so what you can do, if you want to survive a crash or a big fall, something like that, where your momentum's changing a lot, you can use the other definition of momentum. So it's also equal to, and this is the definition, the average force times the time interval over which that force is applied. So since J is constant, what we can do is by lowering one of these quantities, we can raise the other. And so if we increase our time interval over which this force is applied, then the average force felt at any point is lower. And that must be the case in order to keep J constant. Okay, so if we slow impact to increase delta T, this is an example of an airbag. And this lowers the average force felt. Okay, so for example, if you have two identical cars, two identical people, they're going the same speed and they lose control and crash, but one of them has an airbag and one of them doesn't. They will both feel the same impulse. They have the same mass, same initial momentum, same velocity, and they're both going to come to a stop. Okay, so their impulses are going to be the same, even though one has an airbag. The difference is all of the impulse imparted by the forces that are going to stop them. For the person with an airbag, they will be spread out over a longer period of time, and so they will feel less average force and be more likely to survive or less likely to get hurt. The person without the airbag feels, again, the exact same impulse, but in a short amount of time, and so they're likely to feel some extremely high forces and not make it out. Okay, the first problem that we're going to solve, we have a ball that's attached to a spring, a vertical spring, so from some ceiling or something like that, and I didn't draw a ball. And when it's compressed, it's also some height, 3.2 meters up from the ground, and this spring is compressed some distance delta L or X, 0.05 meters. Okay, and we want to find the speed that this ball has when it hits the ground. So this is a conservation of energy problem. So at the end, it's not going to be rolling. It has nothing to roll on. It's going to be in the air the entire time. So it has no rotational kinetic energy, but it is translating when it hits the ground. So it's going to have kinetic energy, rotational or translational kinetic energy. So 1/2, it's a rigid body, so I'll use capital M V squared. And then that's going to equal its initial energy. Well, initially it's not moving. It's attached to the spring and it's being compressed. So it has elastic potential energy from the spring plus some gravitational potential energy from it being off the ground or some above some y equals 0. Okay, so I'm going to start off by multiplying by 2 just to clean this up a bit. So this one, I'm going to do this on both sides. So this becomes mv squared kx squared plus 2 mgh. So that gets rid of all my fractions. And now I just want to solve for velocity. So I'm going to first divide by m. So I get kx squared plus 2. The second term is going to lose its m. So the m on the bottom of this one. And then I need to take a square root. And then we were given our spring constant, so it was going to be 399 newtons per meter. Our displacement for our spring is 0.05 meters. That needs to be squared, divided by the mass. That was also given. It's 12 kilograms. And then plus 2 times 9.8 meters per second squared. And then let me move this over a bit. Oops. Oh, that's okay. and then our height is 3.2 meters. And if you plug that in, you get 7.92 meters per second. Now for the second part, we're going to have this same ball attached to a vertical spring. But now we're going to imagine that it falls on a hill. Okay, I'll move this over. Now we're going to imagine that when it's released, it falls on a hill. So now it can start to roll and translate. So it's going to be rolling without slipping down this hill. And so we need to do the same thing. So first off, let me write what I know. So my K is 399 per meter. My delta L, or X, is still 5 centimeters, or 0.05 meters. My height is still 3.2 meters. Mass is 12 kilograms. And so I still want to do conservation of energy. The only difference is now I'm rolling without slipping, so I'm translating and rotating at the end. So you have 1/2 mv squared for the translational kinetic energy, and then we have 1/2 I omega squared for the rotational kinetic energy. And then initially we have the exact same potential energies as we had in the previous part. So 1/2 kx squared from the spring and mgh from gravity. And so we need to do some substitutions. So the moment of inertia of this disk, I've been calling it a ball, but it's a disk, is 1/2 mr squared, and omega is going to be v over r. So if we plug those in, we get 1/2 mv squared plus 1/2, and then for I, I'll put in 1/2 mr squared, and then for omega, I'll put in v squared over r squared. Okay, and then I'll just write my terms on the right. So now if I simplify, this r squared and this r squared will just go to 1, so it'll disappear. And I'll have 1/2 mv squared. 1/2 and 1/2 is a fourth, so 1/4 mv squared equals 1/2 kx squared plus mgh. So if you add the terms on the left hand side, you have a quarter, you have a half plus a quarter, or 2/4 plus 1/4, so that will give you 3/4 mv squared. And now I need to solve for v like I did in the previous part. So I need to multiply by the reciprocal, so I'm going to multiply by 4 on top to get rid of the 4, and then 3m on bottom to get rid of the 3m on top. So I'll multiply by the same thing on both sides, so 4 over 3m. Okay, and so when I distribute that, all of this is going to go away, and I'm left with v squared equals, I'll just write this in so we can see how everything cancels, 1/2 kx squared plus 4 3m mgh. So here, this 4 and this 2 will just go to 2, okay? And then my m's over here will cancel. And then I'm just going to take the square root. So v is the square root. So I have 2 kx squared over 3m plus 4gh over 3. If you wanted, you could get a common denominator to multiply by m on top and bottom for the term on the right, but it's not necessary. Most people will probably end up punching this in their calculator separately, each term separately anyway. So this is 2 times k, which is 399 newtons per meter. X is 0.05 meters squared divided by 3, 3 times 12 kilograms plus 4 times 9.8 meters per second squared. height 3.2 meters divided by 3. And if you plug all that in, you get the velocity is 6.47 meters per second. So one thing I want you to notice is this velocity is a little bit lower than the one we got in the first part, even though it started with the same potential energy and it reached the same height, it fell to the ground the same distance below, but now it's going slower, and that's because some of that energy that was going to get converted into kinetic energy went into rotation. In the first part, all of the potential energy went into translational kinetic energy, where now some of it is rolling and associated with the disk spinning about its center of mass. And so you get a smaller translational velocity. The next problem, we have chunk A. It's moving to the right, and it's going to hit a chunk B that is initially not moving. And so this is my initial state. My final state, they collide, and then A goes off at 1 meter per second at an angle alpha equals 30 degrees. This is A, and then B is going to go the other way, but we don't know B's final velocity or its direction. And so we want to find both of those. And so this is an elastic collision, so we want to use conservation of momentum, and it's happening in 2 dimensions. And so that means momentum is conserved in the x direction and momentum is conserved in the y direction. And so we want to break these up. So we'll start with the x direction. The final momentum in the x direction is equal to the initial momentum in the x direction. And so in the end, object A is moving to the right, and it makes this triangle. So this is our hypotenuse, VAF. This is our angle, 30 degrees. And we're interested in the x component, so this is VAF x. And so this will be MA times VAF. And the x component is adjacent, so we'll pick up a cosine. Okay, so this is VAF x is equal to VAF cosine of theta, and that's just me using my right triangles and definition of sine and cosine. Okay, and actually I'll go ahead and plug in the 30 degrees. Okay, and it's positive. And then we have the x component of B, but I don't know what it is, so I'm just going to put MB, and since I'm solving for the x component, not the magnitude, I'm just going to write it as VBF x. And then that will equal the initial momentum in the x direction. Initially, B is not moving, only A is moving, and all of the velocity is in the x direction, so I can just do MA VAI. Okay, and that's something that is given to us, and it is 2 meters per second. Okay, so now I just need to solve for the x component of B's velocity. Okay, so I need to move this over, so I need to subtract it, and then I need to divide by everything in front of VBFX. So if I do that, I get VBFX. So I'm going to get the thing on the right, MA VAI. I need to subtract off MA VAF cosine 30, and then I need to divide by MB. Okay, so now if I plug numbers in, I get the mass of A, which is also given, so I write it, mass of A is 5 kilograms, mass of B is 3 kilograms, so 5 kilograms times 2 meters per second minus 5 kilograms, so you could factor out the mass if you wanted to, times 1 meter per second. I need to give myself some more room. and then times cosine of 30, all divided by 3 kilograms. And that comes out to 1.89 meters per second. So this is the x component, so VBFX. And now I need to do the same thing with the y component. So move that over. So now we need to do the same thing in the y direction. So we get PFY equals PIY. This one's a little bit easier. So you get something that looks very similar on the left-hand side. So you have mass A that is moving up, so it's positive. And the x component was cosine 30, so the y component will be sine 30. And then I could put in a minus sign here, but I'm going to leave it. So imagine we don't know what direction the y component of velocity or momentum of object B is. We'll just put mb times vb fy. And if it's going down, it's going to come out negative. If it's going up, it's going to come out positive. Okay, so this equals 0 because initially A is only moving in x, B is not moving at all. Okay, so now I need to solve for VBFY. So I'm going to move this over and divide by this just like I did before. And so I get VBFY is equal to minus MA VAF sine 30 divided by MP. And if I plug in, I get minus 5 kilograms to 1 meter per second times sine 30 divided by 3 kilograms. And I get a minus 0.83 meters per second. So that tells us that at the end, B is moving to the right because it has a positive x component of velocity, and it's moving down. And that makes sense because initially we only had a positive x momentum, or momentum in the positive x direction. If you look at the final state, one goes up and one goes down, so their y components effectively cancel, and then their x components kind of add. So that x component momentum initially was split amongst the two particles, or the two objects, the two chunks. And so their x components are kind of sharing that momentum in the x direction. So now that we have both VBFX and VBFY, we can find, just write these, we can find the magnitude and direction. So we can use Pythagorean theorem. First, I want to draw my triangle. So it has a positive x component. So this is VBFX. And it has a negative y component. And so the overall velocity is going to be down and to the right. And when I look for the direction, this is the angle I'm looking for. Okay, so now if I want the magnitude, VBF, I just do Pythagorean theorem with the x and y components. So VBFX squared plus VBFY squared. So this is 1.89 meters per second squared plus minus 0.83 meters per second squared. If you plug that in, you get 2.06 meters per second for the magnitude. And for the direction, we'll do inverse tangent of, in this case, opposite over adjacent, or y over x. So VBFY over VBFX, or tan inverse of, I'm going to do just positive numbers, and then I know my angle is below the x-axis. So this is going to be 23.7 degrees. And because I plugged in positive numbers into inverse tangent, I get a positive angle. But I know this angle is below the positive x-axis, and that's always the easiest way to do that. So now we want to find the magnitude of the impulse on A and B. So we'll use the fact that, start with B since it's shorter. The impulse is equal to the change in momentum. And this one's easier because This is just final momentum minus initial momentum, and B started from rest, so the initial momentum is 0, and that gives us the impulse is m VBF, or 3 kilograms times the magnitude that we just found, 2.06 meters per second, and that equals 6.2 kilograms meters per second. So that is the impulse for B. Now for A, that does have an initial momentum, we want to break this into components. So impulse is a vector, so it has both x and y components. So I'll drop the vector hat since I know I'm talking about the x direction. So this is the change of momentum in the x direction, or pfx minus pix for object A. And so if I factor out the mass, this is just the mass of A times v final in the x direction minus v initial in the x direction. So this is 5 kilograms. V final was 1 meter per second. And then if we want the x component of the final velocity, then we need to do cosine of 30 degrees. Okay, so this whole thing is VFX. And then we need to subtract off the initial velocity. It's all in the x direction, so that's just minus 2 meters per second. I can close my brackets. And this is minus 5.67 kilogram meters per second, so same units as momentum. So let me move this over a bit. And now we can do the y component. So the y component is about as easy as the impulse for object B. It's the change of momentum in the y direction. So that's pf y minus piy. But initially, object A is moving only in the x direction. So the initial momentum in the y direction is 0. So this is just ma vfy. And again, I'm dropping my subscripts on the velocity, but I know I'm talking about object A. You may want to be more careful about this if you're doing it on an exam. And so mass A, and then the y component of the final velocity is going to be final velocity of A times sine of 30 degrees. And if we plug that in, we get 2.5 kilogram meters per second. And now we can find the magnitude of the impulse for object A just by using Pythagorean theorem. So we have an x component of a vector and a y component of a vector. So we can combine them by just doing jx squared plus jy squared, taking the square root. And that gives us the square root of minus 5.67 kilogram meters per second, all squared, plus 2.5, running out of room, 2.5 kilogram meter per second squared, and we get 6.2 kilogram meters per second. Okay, so one thing to notice is we got the exact same impulse, magnitude of the impulse on object A as object B. And that's because we consider them both a system. And so since they were a system, the momentum, an isolated system, they were only interacting with each other, momentum was conserved. So however much impulse was imparted from A on B, the same amount of impulse was imparted from B on A. Okay, so it's kind of like a Newton's third law going on, but here for impulse. And that has to be true for momentum to be conserved. Now we want to find how long the collision lasted if B feels a force of 500 newtons. So we'll use our definition of impulse. J equals F average times delta T. So delta t is going to equal the impulse over F average. And if the impulse was found to be 6.2 kilogram meters per second, and the average force it gave us was 500 newtons, that means that the collision lasted 0.0124 seconds, or you could call this 12.4 milliseconds. And now if we want to see if chunk A feels the same force, well, we can do the same expression, J equals F average delta T, and we kind of can expect the answer. F average is just J over delta T, and we know they have the same impulse. We found that before. But also, however much contact A had with B, that's how much contact B had, or how long B had contact with A. Okay, they're only colliding when they're touching each other, so they share the same time interval for the collision, or for when this force is being applied. And so if you do this, it's just kind of undoing what we did over here, and you get 500 newtons. Okay, so they both feel the same force, and again, this is kind of a restatement of Newton's third law. They both exert the same amount of force on each other, so they feel the same impulse and change each other's momentum by the same amount. Therefore, momentum is conserved because it's equal amounts. They kind of cancel each other. Okay, so this is Newton's third law. So that means F A on B, little b, is equal to F B on A. Okay, and then you get same impulse and same average force because you have the same time interval. Okay. In the next problem, we have a turntable spinning at a constant 70 RPM. So I'll draw that turntable. It is rotating with some omega, and that omega, second right, is doing another color. Omega is 70 RPM, or revolutions per minute. I already know I'm probably going to need this in radians per second. So this is 2 pi radians for every 1 revolution, and 1 minute is 60 seconds, or 7.33 radians per second. And then my time was 3.8 seconds for it to reach this angular speed after it's turned on. Okay, so if it's going to reach this speed after 3.8 seconds, after it is turned on, that must mean it started at 0 radians per second. Okay, and we want to find the angular acceleration. So this is a kinematics problem, but for angular quantities. So if we look at our shortest equation, omega equals omega naught plus alpha t. We know omega naught is 0. We know omega, we know t, we're looking for alpha. So this is the obvious equation to use. So it's just omega over t. And that's 7.33 radians per second divided by our time of 3.8 seconds. And that gives 1.93 radians per second squared. Now for the next part, we want to find the number of degrees it turns through while speeding up and how many revolutions this is. So then we can go to this equation, delta theta. Okay, so we're looking for an equation with delta theta, and we know time, so we might as well use the one that has time. It also gets simplified by the fact that we know omega naught is going to be 0. So that goes away, and we just get delta theta is 1/2 alpha t squared. So if I plug in, I get 1/2 times alpha, 1.93 radians per second squared, times our time, 3.80 seconds, that's squared, and that equals 13.9 radians. So if we want this in degrees, 13.9 radians Well, there's 360 degrees for every 2 pi radians. And then we plug that in, and we get 796.4 degrees. And we could either go from degrees to revolutions, or we can go from our radians to revolutions. It doesn't matter. I'll go from radians to revolutions, so just divide by 2 pi. And you get 2.21 revolutions. Next problem, you have this rod, this thin uniform rod. It's got a pivot point at the ceiling, and it's making some angle with the vertical. So this is an angle 45 degrees, not drawn to scale. The length is 0.7 meters, and its mass is 2 kilograms. And we want to find the initial angular acceleration after the rod is released. So if we think about it, there's no forces touching the rod when it's released. The thing that's going to cause it to rotate is its own weight from gravity. And so we need to put the force from its weight. So I'll draw that going straight down. So this is its weight, mg. And we need to put that at the center of mass of the rod, since it's a uniform rod. And so our distance, if the length is 0.7 meters, our distance from the center of mass is 0.35 meters. Okay, and now we can find the torque from gravity. So the torque from gravity is equal to Rf sine phi, where phi is the angle between R and F. Okay, so if we do that, so first I want to draw my vector R, so it's going to point from the pivot point down to where the force is being applied. So from the pivot to the center of mass. So this is my RCM. And then the weight, which is going to be my force, is going straight down, so I want to draw that from the same point. And then this is the angle phi that's between them. So the angle that's given turns out to be the angle phi that I'm looking for. So now I get the torque from gravity. If I replace this, this is going to be R to the center of mass. My force in this case is the weight, and this is going to be sine of 45 degrees. So if I plug in my numbers, I get 0.35 meters times the mass, 2 kilograms. G is 9.8 meters per second squared, and sine of 45 degrees. And we get 4.85 Newton meters. Okay, now we know all of the torques. There was only one torque acting on the rod that would cause it to accelerate. And so in order to find that acceleration, we need to use Newton's second law for rotation. So if we sum up all of the torques on a rigid body, that should equal I alpha, the moment of inertia, times the angular acceleration. And since the torque from gravity is our only torque, then we can just solve for alpha. And this is our torque from gravity over the moment of inertia. If you want, you could go ahead and find the moment of inertia. So it's a thin rod rotating about an axis at its end. So that's given by 1/3 ml squared, which is 1/3 times 2 kilograms times 0.7 meters all squared, or 0.327 kilogram meter squared. So if we plug that in, we get the torque from gravity, 4.85 Newton meters, divided by 0.327 kilogram meter squared. So our alpha equals 14.8 radians per second squared. So keep in mind, it's important that it says the initial acceleration. As this rod starts to rotate, this angle changes, and so the torque from gravity is also going to change. And so this acceleration isn't constant, even though we're going to assume it's constant for the rest of the problem. So if the problem didn't state that, you should know this angular acceleration won't be constant, and you can't use your kinematics otherwise unless it's stated. It says if the rod does move with constant angular acceleration, find how long it takes for the rod to rotate through pi over 3 radians. So our delta theta is pi over 3 radians, so you need to be able to recognize that that is an angular displacement. We know our omega naught, it's going to start before we let it go. It's not going to be rotating. And then we just found the acceleration is 14.8 radians per second squared. And we're going to look for the time it takes. Okay, so we go to our kinematic equations, find one that has all of these. Okay, it turns out this one, delta theta equals omega naught times t plus 1/2 alpha t squared, has everything we want plus what we're looking for. Also, this term goes away since omega naught is 0, so that makes things nice and easy. So if we solve for time now, we're going to multiply by 2, divide by alpha, take a square root, and that's going to be the square root of 2 times pi over 3 radians over 14.8 radians per second squared. And it's going to take 0.38 seconds for the rod to rotate through this amount of angle. And then finally we want to find the angular momentum of the rod after it's rotated through that angle. So the angular momentum, L, is equal to I omega. And so we know I from the previous part. So I from the previous part was just 0.327 kilogram meters squared. So we need to find omega. But we can use that since we're assuming angular acceleration is constant. We can just do another kinematic equation. Okay, so omega equals omega naught plus alpha t. We now know how long it's going to take. So omega naught is 0. So we can just plug in. Omega is equal to alpha, 14.8 radians per second squared, times the time, 0.38 seconds. That gives us an omega of 5.624 radians per second after it's rotated through this angle. So now we just plug in. We have 0.327 kilogram meters squared times 5.624 radians per second. And that gives us an angular momentum of 1.84 kilogram meters squared per second. So that's it for this review of energy, momentum, and rotational motion and rotational dynamics. I hope the concepts are a little bit more clear, and these solutions help you get through the practice problems. So feel free to let me know if you have questions, and I'll see you later.